Welcome back to the Demystify Sci podcast. I'm Michael Shiloh.
I'm Anastasia.
And today we have a real treat for you. We have Dr. Erik Zirnstein from Princeton University, who studies the heliosphere. And this is a really important conversation because it fits into a broader discussion of how these different systems matter to us here on Earth. A couple months ago, we talked to Nir Shaviv, who had some interesting correlations between cosmic ray abundance as the Earth moves through the galaxy and climate here on Earth. And a big player in that discussion is the heliosphere, because the heliosphere shields us from these cosmic rays, which are potentially very dangerous to us on Earth, but also seem to play into the nucleation of clouds, which of course feeds back and leads to all sorts of interesting climate cycles that we're still trying to understand here. So it seems like if we really want to understand how things unfold on Earth and how they historically have unfolded at geologic timescales, we have to really understand not only how the cycles play out on Earth, but how those causes might extend to the sun, to beyond the sun, to interactions with other star systems even. And that's really where we're trying to push the discussion here today, is imagining the outer reaches of our solar system and how potentially solar systems could be influencing one another, although that is a bit beyond Dr. Zirnstein's work.
If you like what we do, tell a friend, leave a comment, join us at our Discord. If you really like what we do, join our Patreon at patreon.com/demystifysci. We would love to be able to do this full time, and with your help, that seems like a very, very achievable goal.
And thank you to the people who are already supporting us. It is a wonderful little community, and we've been getting together every Sunday for many, many months now, and it is absolutely the highlight of our week. So we hope to see you there.
And if you don't want to show your face, and if you don't want to let us hear your voice, that's totally fine. You can become a patron and come to these Sunday chats and just spend the entire time in the chat window. There's plenty of people who do that too.
Yeah, lurk away. Enjoy this conversation, and we will see you next time.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
There's two stages to understanding anything, really, right? Which is, number one is creating a model for what's happening so that you can actually have something that you're looking at. And then I feel like the step after that is to start to ask the fundamental questions of why certain things happen inside the model.
Structurally.
And causally, too, right?
Especially when it comes to physics, right?
Yeah, I mean, I've been reading a lot of economics books for whatever reason, and so something that I've found repeatedly is that economics does a really good job of modeling some set of interactions, but oftentimes there isn't, it seems almost a different discipline to ask, okay, well, what's causing this interaction? What's causing this event?
That is such a great question, and I didn't know when we would get to this, because it basically leads to the fact that we have different groups that simulate the heliosphere and get different results with the same input conditions.
Okay.
Unexpected. Yeah, it's unexpected, and it's kind of unfortunate in the sense that, okay, that tells us we are definitely going to disagree, these different groups, but it also tells us we don't actually know maybe what's happening inside the code completely, because you essentially set boundary conditions. You say, okay, I want the sun to have this kind of solar wind coming from the sun to have this kind of property, and the other boundary condition is very far from the sun, far from the heliosphere that we expect. A couple thousand AU is the interstellar medium. And the sun and the solar system are moving through the local interstellar medium at relatively 25 kilometers per second. And, or you could say that we're stationary and the interstellar medium is coming at us at 25 kilometers per second. So in these simulations, we have a stationary sun with solar wind coming out of it, and then basically a boundary condition of a wave of interstellar plasma and neutrals with certain temperature, speed, densities, and you just let it run. And depending on how you start it, and depending on the source terms, which means like how do neutral particles interact with ionized particles, they can transfer electrons between each other. That really greatly affects the size of the heliosphere. And how long you run your simulation, whether you try to reach a steady state or quasi-steady state, or if you actually have time-dependent boundary conditions. All of these little things can cause great differences in the simulation output. So this has caused us to have arguments within our community on interpreting, for example, IBEX data, which tells us certain things about the sky, maybe like how far away certain boundaries of the heliosphere are. But people interpret the same data differently depending on what simulation you use. And recently it's become kind of difficult to tell the difference between the simulations, even though the simulations look different. If you simulate ENAs coming out of your simulation and compare it to the data, they're not that much different.
When you say ENAs, what does that mean?
Energetic neutral atom. So this is the main source of particles that we use to understand the thermodynamic properties of the outer heliosphere, but also the size and shape of the heliosphere. Sort of in a nutshell, as the solar wind propagates radially away from the sun at speeds ranging from 300 to 800 kilometers per second, could be faster if it had a like coronal mass ejection or something. It's moving very fast, and the interstellar medium, part of it is neutral gas. And because they're not affected by magnetic fields, they can just easily propagate into the heliosphere. And one of these neutral atoms can charge exchange with a very fast moving solar wind proton. And they exchange an electron. So now you have a fast moving neutral that's just going to ballistically leave the heliosphere. And it's replaced by what we call a pickup ion, interstellar pickup ion. And based on how it's picked up, it was like a slow neutral. And then all of a sudden it's ionized, and there's this fast plasma moving by it that causes a motion electric field that then picks up this ion, and it has a very large thermal spread in the moving plasma frame. So it's actually kind of a hot distribution.
What's the direct readout of that? Is it a thermal signature? Because usually you think of neutral hydrogens as being optically transparent. So it's fascinating that would be the primary marker player in this game. So you're looking at these indirect. Okay.
Well, actually, okay. So we do observe these interstellar pickup ions in the solar wind with New Horizons. The SWAP instrument on New Horizons can measure solar wind protons, alpha particles, and interstellar pickup protons. And we create these, basically can fit distributions to our count rates that we observe and understand that their density, mean energy, or temperature, and understand their adiabatic or non-adiabatic nature within the solar wind. But it's this composite of solar wind protons and new embedded interstellar pickup ions that have a much broader distribution, that they flow all the way to the heliospheric termination shock, which is the first outer boundary of the heliosphere. They become the the pickup ions themselves, they're now about 25% of the number density of the plasma. They become preferentially accelerated by mechanisms, could be shock drift acceleration, diffusive shock acceleration, all sorts of stuff that involves turbulence and reflection from shocks. And there's been many studies on that. But basically, once they cross
interactions, could we just say interactions with the ISM? Are these interactions with external stuff?
Still not in the ISM.
Still not there.
It's
what are they shocking against, I guess, is the question.
Is it the magnetic field?
The solar wind is moving supersonic, as in the flow speed of the particles is a lot faster than any of the sound waves or Alfvén waves, the magnetic oscillations that, basically if you're moving subsonic, then you're moving slower than information that could warn you if something is coming up ahead. So you end up slowing down early if you're going to meet with the interstellar medium. But because the solar wind is so fast, there are no waves that can travel ahead of it to warn us, to warn the solar wind that, hey, we're going to collide with something. And then all of a sudden we get so close, pressure builds up, and then a shock forms. A shock has to form. And it forms all around the sun.
It sounds like it's kind of the equivalent of like if you drop something off of a bridge onto water below, like the way that it hits the water is almost like a solid object, and it's more force than it would be if it was moving through something more viscous, because it would be slowed down by the interactions of the viscous fluid against the surface of the water.
I suppose that's one analogy. Another one could be a jet that's flying through the air, and if it's fast enough, you'll see a bow shock ahead of it. That's just because the jet is moving so fast that any of these, the speed of sound, literally, it's moving faster than the speed of sound, Mach 1 at least. So the literal obstacle is the jet, the front of the jet itself, and the air ahead of it cannot see it because the sound waves in the air are moving much slower than the jet itself. So a shock forms ahead of it. Or like a boat, you will have a bow wave ahead of the boat if it's moving fast enough.
It's like the particles can't get out of the way fast enough, and so they just pile up. That's a way to think about it. They are not formed enough in time that they end up piling up, slowing down really quickly. This slowdown is less than 1 AU in size compared to the huge size of the heliosphere. They're compressed because of this slowdown, so they become compressed and heated, and certain particles, the pickup ions, have a wide distribution in velocity space. So they have larger speeds and going in different directions in phase angles that they can actually interact with the shock front and basically surf along it, gaining energy as they do that, because they interact with a moving motion electric field. Like they bounce back into the solar wind pushes them back into the shock, gain a little energy, and then once they gain enough energy, then they go downstream. So downstream of this shock, and then remember, this shock is surrounding us in all directions. It's not a sphere, but in simpler terms, you could see it's almost a sphere, but offset. Like its sun is closer to the shock near the forward motion of the heliosphere into the interstellar medium,
and then towards the tail direction, the shock is farther away. But beyond the shock, this plasma has become heated. The interstellar pickup ions have been accelerated. They produce superthermal distribution. And it's that source of particles that those particles then can neutralize by charge exchange with another interstellar neutral that comes from outer space. And some of those neutralized superthermal ions from the heliosheath, which is the region between the shock and the edge of the heliosphere, the heliopause, some of those can travel back towards us, to the sun, to Earth, to the IBEX spacecraft, and be observed. So the plasma has to be hot enough such that once particles are neutralized, they can have trajectories going in many directions. Some of them come back towards us, and then we can measure them.
The whole process reminds me of like rubbing a balloon on a piece of wool or something. It seems like there's almost a triboelectric process here where there's these frictional interactions at the interface that are leading to all of this charge. Is that a reasonable way of looking at it?
Not really what I would think. The only sort of current interaction that I think of when we hit this shock is because the solar wind not only has ions, but also has electrons. So if you want to assume quasi-neutrality, let's just say that there's solar wind protons and electrons. Protons have a much larger mass. Electrons are very low in mass. And as they are being reach the shock and being slowed, the momentum of the electrons and protons are different. So one will overshoot and create this, I guess you can say temporarily creates a current, but what it actually creates is a potential, electric potential, a standing potential at the shock. And this potential actually also is partly why some pickup ions are accelerated at the shock. Because some of them in their certain part of velocity space, as they reach the shock, they were actually going sort of backwards towards the sun and have very low velocity in the shock frame. So they can't cross it. This potential is holding them back. So they're going to surf along the shock until they gain enough energy to then go downstream. So there is this cross-shock potential that also plays a role in this formation of a hot plasma in the heliosheath part.
This is such a biological system almost, because in a cell you have a membrane potential, and that membrane potential is instrumental to keeping things inside of the cell versus outside of the cell. And so it seems like what you're saying is that there's this electrical barrier that's at the very edge of the solar system that is permitting some things to remain inside, or forcing some things to remain inside, allowing passage to some other things, and then exchanging from the interstellar medium other content.
That's true, except eventually all particles can go across the shock. All will eventually. The ones that are held back more will gain more energy and then go across the shock.
So there's no retention of anything. Basically, anything that the sun puts out inherently will always leave. There's
no net mass retention, held upstream of the shock. However, that comes to the next boundary, the heliopause. So after the solar wind, all of it has eventually, let's talk about a parcel of solar wind. Has crossed the shock. Now it is compressed, slowed, heated, and it is now subsonic. It is very hot, but the bulk flow of it is moving a lot slower than the sound wave, magnetosonic sound speed. Because of this, the heliopause is actually formed as a tangential discontinuity, which separates the solar wind plasma, which has a magnetic field. And that magnetic field is completely disconnected from the interstellar medium's magnetic field. So it has to also create this tangential discontinuity we call the heliopause. Ideally, as this parcel of heated plasma approaches the heliopause, it is deflected around and then down the tail. It just can't cross it. That's the barrier. No mass can cross the heliopause. Sorry, and that's the same for the interstellar plasma. It is approaching the heliosphere, the heliopause. It also becomes compressed and heated. It has its own shock, bow shock. And when it gets close enough, it diverts around the front and then flows around the sides and back.
What's going on with the interaction between the magnetosphere and the interstellar? What did you call it? The interstellar magnetic field? So
the heliosphere and the interstellar magnetic field, that is one of the most interesting parts of the research that I've done, and has been one of the connections between Voyager measurements, like in situ measurements where the Voyager spacecraft are, and then IBEX measurements. So what happens is, whatever orientation the interstellar magnetic field is, we assume at such large scales, we assume in our local interstellar medium, far enough away from the heliosphere, it has one single direction, one vector, the B field. I'll just call the B field from now on, magnetic field. It has a certain strength and a certain direction. And it's being carried in the frame of the sun. It's being carried with the interstellar plasma up into the heliosphere, and the magnetic field also becomes compressed. And depending on what the orientation of the field is in our local interstellar medium, it'll become compressed. What it actually does, it becomes compressed below the nose of the heliosphere. The nose is what we call where we're going relative, where the solar system is moving relative to the local interstellar gas around us, and causes a higher compression below us. So we think there's this asymmetry, and it kind of pushes the heliopause inwards a bit because it has a higher magnetic pressure outside. But the orientation and how the field drapes around the heliosphere, it kind of drapes and shapes it a little bit. We are able to sort of determine pretty accurately what that field configuration is far from the sun. So the pristine interstellar magnetic field, magnitude and direction, using IBEX observations of the ribbon. Now, the ribbon was an unexpected discovery that IBEX made in 2009, the first measurements we made. So IBEX launched late in 2008, did some commissioning for a few months, testing, calibration. And then when it started making measurements, what we expected was higher ENA fluxes from the front of the heliosphere, where it's more compressed and it has a hotter plasma. So you would create higher emissions of these ENAs, and then low emissions on the sides, but then a slight increase in emissions from the tail, because the tail is so long that you can just have more time to create more ENAs that you can measure over time. But we also saw this, on top of that, we saw a band that's about 25 degrees wide that crosses between the Voyager 1 and 2 spacecraft. So if you plot a sky map and you say, okay, Voyager 1 is going in this direction, Voyager 2 is going in that direction, right between them, halfway, there's this narrow enhanced band of ENA emissions wrapping across approximately 300 degrees of the sky, so most of it.
Whoa.
And we see it in every energy channel of the IBEX high instrument, which measures particles moving with kinetic energies between 0.5 keV and 6 keV, but it really peaks at about 1 keV, which is...
Can you explain the significance of that?
The significance of that is it peaks at 1 keV and 3 keV. In one of our, the spacecraft has electrostatic analyzers that basically step through what we call pass bands, allowing particles with certain energies to actually enter the instrument. So we can say particles between 0.5 and 0.8 keV were able to come into the instrument. We measured them. Here's the amount of flux. So we have different energy channels. We saw high emissions at around 1 keV and 3 keV, but particularly the 1 keV is at low to mid latitudes, near the ecliptic plane and up and down about 30 degrees. That is where the slow solar wind is primarily located over most of the solar cycle, especially at solar minimum. And the speed of the slow solar wind is about 400 kilometers per second. That's about 1 keV.
And this is essentially the plane in which the planets lie as well?
Exactly.
I see.
The solar equatorial plane and the ecliptic plane of the planets is only tilted by 7.5 degrees. So essentially it is up and below the ecliptic plane of the planets, right?
Now, is that significant in terms of organizing the bodies into this plane? Or is that still,
the rotation, I believe, of the sun as it formed was the primary reason. The angular momentum is why they created this ecliptic plane. So that's probably why they're so close. The solar equatorial plane and ecliptic plane.
But the fact that you said that it's this tilted, you said it's a ribbon, right? So it's not a flat, it's not just a flat pattern in the ecliptic where you have slow solar wind at the equator and then gradually moving faster and faster. It has a twist to it.
Exactly, yes. So the places in the sky that we see it has nothing to do with the solar wind. That has to do with the interstellar field. But the amount of emissions at certain energies that we see it has to do with the solar wind. So we see a lot of parts. So just imagine that the ribbon is just in one place in the sky at all times. But we see a lot of 1 keV emissions in the low latitude part of the sky because if you remember when I said before, the solar wind coming out from the sun can range between 300 and 800 kilometers per second. And most of the time it's between 300 and 500, on average 400 at low latitudes. And that's 1 keV kinetic energy. So what's actually happening is these solar wind protons moving at 400 kilometers per second, an interstellar neutral hydrogen atom came in really slowly. They exchange an electron. So this fast-moving solar wind proton is now neutral and just ballistically shoots outside the heliosphere. Because the only thing that can stop it is another ionization. But the ionization rates for those speeds of neutral particles is so low inside the heliosphere. Only until it gets outside the heliosphere that it will ionize again, because the interstellar medium, as it compressed close to the heliopause, is much more dense than inside the heliosphere. So this neutralized solar wind proton travels outside the heliosphere, and they travel in all directions because the solar wind, is going in all directions, and some of them are neutralized, and then they just continue going radially outward. However, the ones that go towards directions that are perpendicular to the local interstellar magnetic field. Imagine you have a neutral going out, and at some point it ionizes. And if it ionizes close to when it ionizes and creates a new ion, if that ion has a large pitch angle, that means it ionized close to where our line of sight is nearly perpendicular to the local interstellar magnetic field.
Yeah, we didn't talk about the orientation of the interstellar magnetic field yet, but I am very curious about how it compares to ours.
The fact that we can only see the ribbon where we are looking perpendicular to the interstellar field draped around our heliosphere. So if you actually moved yourself to, I don't know, Pluto or some other vantage point, plot the same sky map, take another observation, the ribbon would move.
So it's an artifact of the way that you're looking.
Exactly. It's sort of an artifact of how our vantage point.
So does that mean that it becomes less significant? Because I mean, like you see, because as far as I understand it, so does this relate to the maps of the heliosphere that you see that it looks like it's this like curved ribbon-like substance that is extending in all directions away from the sun? Is that the same thing? Do you know what hold on, what is that called?
I think it's called the
current sheath or something?
Heliospheric current sheet.
There you go, yeah.
Yeah, no, that's not very related.
Okay,
yeah.
All right.
I mean, my question is how, obviously magnets interact with one another in very well characterized manner. How is this playing into the organization of our star with respect to its environments? Is there polar agreement? Are they, it seems like it must be playing a role in some sense in terms of orienting the stars with respect to the ISM.
Do you mean the dipolar nature of the sun?
I guess so, yeah.
How it might interact with our local interstellar medium?
Yeah.
So it mostly influences how the smaller kind of shape of the heliosphere arises, rather than influencing the interstellar medium itself. For example, there is a solar cycle. There's 2 solar cycles, actually. Every 11 years, we have an increase and decrease, and then increase again in the number of sunspots on the sun. And what we also have is polar coronal holes that at solar minimum have, let's say we're looking at the North Pole, has expanded open, and fast wind is moving out from these polar coronal holes. And the speed of these on average is 750 kilometers per second, which is 3 keV, which is why we see the ribbon intensity at high latitudes increase at 3 keV, because those contribute to the ribbon at 3 keV. Just a little sidestep back to what we were discussing before.
Yeah, and the poles are inverting of the sun's magnet, right?
Exactly, yeah. That's a 22-year cycle. During this reversal, I'm not exactly sure how much it affects the overall structure of the heliosphere, but I know it does affect the propagation of galactic cosmic rays and even anomalous cosmic rays, which are locally generated We think they're particles that were pickup ions accelerated to very high energies at the termination shock. But depending on the time in the solar cycle, the 22-year cycle, you can have galactic cosmic rays coming in along the current sheet, heliosphere current sheet, or they'll come in along the poles. Depends on the polarity. And there's some particle drift physics to it that is now going beyond my recollection. But in my mind, it affects you can call it filtration, but definitely the trajectories and distributions of cosmic rays, which, in itself is a very important study for anyone who has satellites orbiting Earth. Cosmic rays can interfere with electronics. You might have heard this before, that the heliosphere itself, the heliosheath, that region between the shock and the heliopause, shields out, I think, 75% of the incoming galactic cosmic rays. If it didn't do that, we wouldn't be here.
Yeah, it seems like there may have been some cosmic ray events that could have shaped evolution on our own planet. We were talking with Nir Shaviv in Israel, who had an interesting hypothesis for how rare cosmic ray events, I don't know if they're related necessarily to the breakdown of the heliosphere at all, but just as the sun makes its way through more dense regions of the galaxy, how that could affect nucleation of clouds essentially on Earth and really toy with the environments and potentially catastrophic feedback loops.
If our heliosphere was smaller millions of years ago, which I know has been proposed by one of my in our scientific community colleague, if it was a lot smaller, then cosmic rays could definitely affect any of the planets that are within the sort of heliosheath region. So if that was happening millions of years ago, that would have affected anything that was going on in terms of development of life, or how the planets were forming, although they formed actually a lot earlier than that.
I mean, I think that they're formed regularly and constantly, and they're being reformed, and there's various changes in environmental conditions that, from a biological sense, have you heard of like biogeochemical cycles?
No, I don't think so.
Well, so the microbial life on Earth is literally metabolizing the rocks that the planet is made out of. And so as you change conditions for what bacteria are able to survive, or let's say just by tuning radiation, you would change the profile of the way that the planet is evolving in this mineralistic way. And because everything is built on the backs of the microbial life on Earth that's providing the raw materials for everything else, then you can imagine that would propagate over long enough periods of time up the entire ecological web to change the profile of life on Earth.
Yeah, so I guess the question would be how much of an impact you would need to have it occur over a noticeable amount of time.
And I think that comes down to how severe of an environmental catastrophe the change causes, right? Because we know that there's these mass extinction events, and our relationship to them is very sketchy, where we know that they're there because we can see them in the record. You have explosions in the fossil record, you have massive declines in the fossil record, but our models for what could have caused those is pretty thin. But we know that after a huge extinction, you then have this radiative event where you fill back up with different species, and those species are distinct in terms of their body plans and their structures and their functions from the ones that came before. And so there must be a back and forth relationship between what's available on the Earth and the creatures that form that feed off of it in the aftermath of something catastrophic. Because you don't get this, like, we didn't get dinosaurs again after the dinosaurs died. And
Right.
We got ice ages instead.
Yeah. And so there's something different that happens, and I feel like it's such a big effect over such a slow period of time that we have a hard time placing it and creating a cohesive narrative, because it requires this sort of almost intergalactic to microbial perspective that no one has, because it seems crazy to join the interstellar medium to the microbe that's breathing the iron, the ferric rocks. But I'm sure that there's a line between them, as jagged as it is.
This actually can be related to the solar cycle itself.
Mm.
I think it was called the Maunder minimum.
Mhm.
The solar activity was so small it caused a mini ice age on Earth. I really should know the date of this. It's, I think, in the 1800s, but don't quote me on that.
I think it was the 1860s. It was like the year without a summer, I think.
Yeah, because the activity is so weak that, not only, I guess, we had less thermal energy from the sun, but we would also have a weaker activity of sunspots and solar wind pressure, and probably the heliosphere was very different, a lot smaller, possibly. That would affect the cosmic rays and everything in between.
The year without a summer was actually something different. It was, I think, from the eruption of Krakatoa. This was 1645 to 1715. So it was more than a year without a summer. But there's the Maunder minimum and the sun cycle actually is really interesting, because you said earlier that with the sun cycle you would expect to see differences in the structure of the heliopause and the interactions of these interstellar ions versus the solar ions. Have we been studying it for long enough to be able to trace how that changes, or is this a relatively new, detailed look that hasn't been able to cross from a solar maximum to a solar minimum and then back again?
Actually, we have just completed with IBEX a full 11-year solar cycle of observations. And we have seen a recovery of ENA emissions. The source of the ribbon is farther away than the source of what we call the globally distributed flux, which is in the heliosheath itself, that hot plasma. And over time, changes in the solar cycle are reflected in the GDF sooner than they are in the ribbon, just because it's farther away. It takes more time to see reflections and changes in the sun. And we have seen people are, still publishing on this right now. Papers that I'm a co-author on are under review that are showing that there is this cyclical behavior of energetic neutral atoms with the solar cycle. And one very, very important event that happened was in late 2014. The solar wind dynamic pressure increased by 50% in a matter of 6 months.
Whoa.
Which was a very strong and global event. And 2 years later, we saw a small, I say small, about 30 degree radius spot on the sky below the nose. ENA emissions just started increasing rapidly. And then over time, year by year, the emissions grew across the sky. They grew sort of north and south first, and then spread sideways. And it was the heliosphere itself responding to this almost global increase in solar wind pressure. And my colleagues and I we basically had this simulation of the heliosphere, and then all of a sudden we just said, solar wind pressure increased by 50%. what happens? It pushes the termination shock outwards, pushes the heliopause outwards, but more slowly. It responds more slowly to it and doesn't move as quickly. They moved about 7, 8 AU for the shock, which is quite a bit, and heliopause up to 5 AU. And by simulating ENAs from this simulation, I showed that if you take then differences between neighboring maps over time, you could see a ring of the reaction just going across the sky, and then the ring reaching the tail 8-10 years later, which we have yet to observe. It's a couple of years from now.
But are you watching it as it's happening, basically go from the front around already, or
We've
are you
seen
not?
it so far go to all the way to the north top, the south, and a bit beyond the south, which kind of seems to us, tells us that the southern part of the heliosphere is closer to us than the northern part. And we saw it go around, I think, all the way to the sides. The unfortunate part is the signal gets weaker and weaker and weaker because A, the heliosphere is farther away, and B, the heliosheath thickness is growing. So the ENA signal is being washed out or is just weaker because they have lower density plasma to create a higher ENA emission. So the signal is being more difficult if you really want to track it all the way to the back of the tail.
I mean, it makes sense because what you were saying earlier is that you had to make these decisions about modeling, like what's staying still versus what's impinging upon the thing that's still. Is it the interstellar medium that's impinging on a stable solar system, or is it the stable solar system that's moving through a stable interstellar medium? But no matter what frame you choose, if there's a direction of movement, you would expect it to get more turbulent in the wake of that movement, right?
Yeah, I think in the simulation sense, it doesn't actually matter which frame you do it in. Pretty much everyone that does these simulations in the sun frame. So the sun is stationary, and then there's just this interstellar medium moving past us. But because of that, there is, you're right, in either scenario, if you think about it, there is a wake behind us, a tail, which is a completely separate controversy on the structure and length of the tail is a controversy. Different models predict different lengths, and it has to do with how you solve it, how you initiate your heliosphere simulation. And
is there any hope of sorting out these different models by looking at other star systems and examining? Because, we learned a ton when we started studying other planetary systems. We kind of learned that our solar system was actually quite an outlier in terms of the organization and so forth. I wonder if we'll have similar revelations when we're able. Are we able to look at other heliospheres? Or
yes, we call those astrospheres, and we can see them in, I think, UV, X-ray, maybe visible light. I'm not sure. Depends on the gas around it that causes the light emissions. And some of them have such long tails, like parsec, much longer than we expect ours to have. The longest simulated heliosphere heliotail that is predicted is maybe 3,000 AU long. Part of the problem with understanding how long it is that our only direct observations are with ENAs. But the process by which ENAs are created depletes the plasma of those energetic particles. So you can imagine that as the plasma flows down the heliotail, it's creating ENAs, but it's losing these particles and being replaced with lower energy particles. So at some point, we're no longer going to be able to observe ENAs. They were all created.
Elaborate on that. I don't quite. They're not constantly
They're
being.
just losing energy, essentially. These transactions are building up and they're being
When you say we're
neutralized.
no longer going to be able to see them, you mean in terms of as you look farther and farther away from the sun?
Yes.
I see. Okay.
Further
Sorry.
down the heliotail, the plasma is essentially cooling, and we can no longer see ENAs, energetic particles, around a keV. And
That makes sense. Yeah.
they're going to be so low energy that they're being observed. Either they could be observed by the IBEX low instrument, which measures between about 15 eV up to 2 keV, but it has more issues with statistics. So we really try to use IBEX high observations to the best as we can. And it turns out that we can say that a minimum distance of the heliotail is 350, 400 AU from the sun. And by that, I mean not actually distance to the heliotail, but rather distance to the edge of the ENA source region that we could observe. However, there are two observations, completely separate observations that have more than hinted that the heliotail is long. One is Lyman alpha observations from stars, that if you happen to have an obstacle between you, the observer, and a star, I don't remember what star is near the heliotail. I think there was a study on this. They could tell that the heliotail was messing with their observations. Like if you look at neighboring stars away from the tail, you see a very specific emission lines. But if you look down the tail, it's obviously distorted because of a very long structure. And I think they could say, oh, it's has to be pretty long for it to mess with these observations. One of my favorite is galactic cosmic rays, specifically TeV energy cosmic rays. There have been studies that show that if you look at these cosmic ray anisotropy maps, which are basically maps showing differences in intensity of these cosmic rays in different directions of the sky, you'll see a little spot near the heliotail, or sort of connected by their trajectory to the tail, that can only be reproduced by a simulation that has at least a few thousand AU length tail.
Wow.
Yeah. So,
but that's relatively small compared to the stars that you're saying have a 1 parsec tail. Because I just looked that up, and that's 200,000 AU.
Yeah.
And so
it's just completely different star. Maybe that the one that has a huge tail also is moving a lot faster than we are. Could be many different things that could differentiate other astrospheres to ours.
How many AU is it to the next star?
I mean,
anybody? I guess we could Google that. I'm just curious.
Light years is what, 4 or 5 light years? Was that right?
Yeah, but how does that translate to AUs? I'm sorry. I don't know the conversion.
Proxima Centauri is the closest star, right?
How many AU?
Hold on 1 second. So it's 4.2 light years.
I'm just curious.
I know the conversion from AU to kilometer, but I don't know parsec to AU.
So 4 light years is 265,000 astronomical years.
Yeah, so it seems like these heliospheres could be directly interacting with each other in that case. Like the tail could be brushing up against the nose of the next. I mean, in these extreme cases, at least.
In some, it could be possible. I don't think it's happening with us. But
okay, so yeah, that's the question, because there's the heliopause and there's the bow shock. The bow shock is on the interstellar medium side. The heliopause is on the sun side.
Oh, the heliopause is the exact boundary between the sun and interstellar side.
Interesting. Okay, so is there something
the
that's
solar
before?
wind or heliospheric termination shock is on
Termination
the sun side. Yeah.
I see. Okay. Oh, yeah. Okay, I can see that now. So there's basically...
And we're not sure even if it's a bow shock. We think it might be a bow wave.
Interesting. Okay. But the question is when we say that it's the interstellar medium that it's the bow shock or the bow wave is in, we don't think that it's the medium of another star? Like we treat the stars as being within their own little envelopes that are separated by true interstellar medium that is completely separated from them, or do we treat the stars as impinging upon one another?
And as far as I'm aware, at least in our location in space, we are separated from any influence of other stars.
How difficult
in this sense?
How difficult would it be to look out onto the sky and to create a map of the boundaries of, 1,000 stars that we can see, that are the brightest stars in the sky?
Like astropause boundaries?
Yeah, exactly.
Oof. I only know of a few examples where you can actually see it, and those are the very extreme long ones.
I wonder if you could estimate it by various parameters related to the solar wind strength of different stars.
I mean, because it's so big, it's surprising that you can't see it for something. Am I just completely misconstruing the level of resolution that we have when we look at stars that are far away?
Well, this particular example of astrosphere is probably very far away. So even though its tail is long, if you actually just put it on a map on a screen, like the gravity wave map or cosmic ray map or our own IBEX maps, you probably couldn't even draw it.
So it's really, really. Yeah, I mean, it's hard to consider distances. There's that scene I think it's in The Hitchhiker's Guide where Zaphod Beeblebrox goes into the infinity machine and he's like forced to contemplate the size of the universe, and it's normally something that breaks people, but he just walks out totally fine. I feel like I have a really hard time just thinking about how big it is.
Well, and the interstellar structures are so tantalizing too, because there's this Oort cloud hypothesis, and I'm curious how that plays into this paradigm as well.
What's the Oort cloud hypothesis?
Well, it's hypothesized that there's some objects that extend further, like almost halfway to, like there's a wall of structures, little or big icy balls of things, right? This is supposedly a reservoir for our comets, and they can extend nearly halfway to, or it's thought to potentially extend halfway to the next solar system. And so if you start thinking about all the stars, if they all have Oort clouds, you really end up with this interesting web of stuff that's out there. I just
definitely know of the Oort cloud. That's definitely true. I think as I discreetly look at a different screen, is between 2,000 and 100,000 AU.
Some of the extreme, so there's different estimates, right? There's like different models. I guess I'm pointing to some of the more extreme estimates of it.
Oh, extreme.
Yeah, I don't know. There's
100,000 AU was what 1-2 parsec? Because it said
I think it's almost a couple light years.
Oh, sorry.
No, 1 parsec is 200,000.
1 parsec is 200,000.
We said 4 light years was 200,000 ish. AUs.
Yeah, but so 1 parsec is 200,000, and so 1 parsec is a little bit less than 4.2 light years.
But at any rate, the Oort cloud is a couple light years away in some estimates, I suppose.
Yeah, so it's like looking at the front page of Wikipedia, the Oort cloud is proposed to surround the sun at distances from 2,000 to 200,000 AU, which is beyond the termination shock and the heliopause. So it's so it's like something that's out there in between the stars and seems to be gravitationally bound to our sun, But it's weird that it's beyond the termination and the heliopause, because that seems like the way that I look at them is to be the limit of the sun's influence. But
Well, that's the limit of the sun's electromagnetic influence.
Mm.
These objects are controlled by the gravity of the sun.
and so that speaks to the importance of the structure and the interaction of these ions and these plasmas, because you wouldn't expect gravitation, like if there wasn't this wall of interaction, you would expect there to still be an electromagnetic interaction at that distance, right? Like if you didn't have the termination in the bow shock, is there any reason that the sun's magnetic sphere influence would stop short of gravitational influence?
Depends on the interstellar medium you're surrounded by. If it's extremely weak, if the interstellar medium is, the local interstellar medium is so low in density, the influence of the sun, the solar wind could extend a lot longer. It would still dissipate over a certain distance. I'm not really sure how far. I bet Eugene Parker calculated how far it could go, depending on the interstellar boundary limits.
I wonder. Go ahead.
I mean, at least in the tail, we believe. I'm a personal believer that the tail can be a few thousand AU in length. That can literally be reaching the Oort cloud. The inner edge of it, maybe.
Yeah.
If it's spherical around the sun.
Well, it's also because if we know that there's changes in the interstellar medium, right? So like as you're moving through the galaxy, as the galaxy is moving through whatever is the, intergalactic medium, you're going to have changes to the interaction of the sun with its immediate environment. And maybe it's like a beach, like the line of driftwood on a beach, where what the Oort cloud is it's the detritus that gets
foam buildup.
Yeah, like the foam buildup of the breathing of the solar system.
I'm not sure.
I mean, because to blame it on gravity is kind of an interesting claim too, because if it's
not
halfway,
blamed on.
hold on. Like if it's halfway to the other star systems, certainly the other star systems' gravity is going to have a nearly equivalent effect on the structure itself. I don't know anything about it, but it seems like gravity is extremely weak at distances like that, and both star systems.
It's possible, I guess, and I'm just shooting from my hips here, but comets that fill the Oort cloud could have come from other Oort clouds.
That's tantalizing.
Exchanging, maybe.
The exchange is interesting because we have a sense of I have a sense of the solar system as being an encapsulated meta object, where it has this sheath to it, where the sheath is protective against the things that impinge from the outside. And yet, I also, in the back of my mind, recognize that there has to be some kind of exchange in between systems. It's hard for me to believe in the myth of the closed system.
I think this exchange would be very rare because of the process of causing a comet to deviate from its path to come to the sun, because usually we see comets that are regulars, right? Halley's Comet and others, I can't name them. Halley's Comet is the only one I know. They're always coming back every 50 or whatever years, and something significant would have to cause them to go off trajectory.
A lot of them get eaten by the gas giants, though, right? I think a great deal of the comets get eaten by the gas giants or by the sun. I feel like we lose a fair amount of them.
Okay,
And there's also this other stuff, which is the unbound planets, which there's some fraction of planets that aren't
Like
part
rogue
of
planets?
rogue planets. Yeah, they're not part of solar systems, so they're floating around, and they're hard to see because they're dark. They're not necessarily passing regularly in
cold.
front of a star, so you can't track them. And I would assume that there's some amount of just wild collisions that are happening that are creating the comets that then get captured by solar systems. And so the exchange wouldn't necessarily be, like Halley's Comet being hit out of the solar system to go somewhere else, but more like the detritus that's on the edge of the solar system ramming into itself or ramming into the detritus from another star system and then being flung outwards to be caught by some other system eventually.
All I can say at this point is I wouldn't underestimate the fact that there's huge distances between these objects. Kind of think of it as like a very dense cloud of comets, asteroids, or whatever, but they're so rarefied that I'm not sure how often they actually would collide.
Yeah, that's one thing I find the students are always shocked about is even when you talk about the asteroid belts, because you look at like movies like Star Wars and they're like dodging all these asteroids and everything, but NASA just sends probes through that thing without even blinking. I mean, there's like 100,000 kilometers between each one of these objects or something. It's crazy.
But I mean, if there's that is something that I wonder about, which is how difficult is it to send something through the asteroid belt, like Voyager 1 and Voyager 2, New Horizons.
It's no issue whatsoever.
I that comes back to my inability
actually,
to grasp
they have to work really hard to try to hit one. New Horizons successfully flew by Pluto in 2015, and then they actually had to find the nearest asteroid. I can't remember its name. A few years after.
Was it Bennu?
That they really tried hard to get close to take images of. And it was like this, I think some people called it like a bath duck shape. It had like one bulge here and one bulge here that was slightly larger, so it looked like a ducky.
I'm looking at it right now. I think they called it Arakoth.
Kuiper Belt flyby Arakoth, right? Yeah.
That's a really, really weird looking glob.
I know.
No, I know.
Is there any sense of what it's made out of? Is it ice or is it?
Um,
The asteroids are mostly rocky. This one, I guess this is... Did you say this is a trans-Neptune one?
I don't know.
This is Kuiper Belt object.
Yes, this is way beyond the asteroid belt.
Well, this is between... Yeah, that's right. It's beyond Pluto, obviously. Yeah.
Yeah, it seems like the objects that are getting a lot of churn out there are very cold and frozen and icy. Like the Oort cloud is supposed to be entirely icy for the most part. I mean, there's some rocky, dusty stuff, but that's kind of the difference between comets and
since the Oort cloud the volume of the Oort cloud is so much bigger, it becomes even more rarefied with objects. Unless for some reason there's more objects to fill the bigger space, but I'm not sure with that.
Yeah, I guess it's interesting. I guess we just can't really answer the question about the churn at this point.
I mean, this is what's so interesting to me about these sorts of sciences is that I studied biology for a long time, and every place that you go to in biology, there's a sense that we've figured out the major paradigms. We know the major players, and our goal now is to just work out how the major paradigms fit together. And I feel like in astrophysics and cosmology, there's a really real sense of discovery. And because I was looking at the press release for the ribbon structure we were talking about earlier, And there's a quote from this guy named McComas, who is in charge of the project. David McComas.
He's my supervisor too.
Okay, so he's the principal investigator of the IBEX project, and he says the last sentence of it is, we have to figure out what physics we're missing because we didn't expect to see this thing here.
Exactly. Yeah.
And that's really unusual in something like biology, I feel like. Where the idea that you would look at something and be like, oh, we never expected to see that is not really how...
And we have to rethink the biology.
Yeah, and we have to rethink the biology. Like, that almost never happens. And yet, when it comes to the physics of stars, I feel like it's a pretty regular occurrence that as we gather more data, there's this sense of, oh, we might be missing something. Like with the... I always think about the example with the Cepheid variable stars, when they first realized that the Milky Way wasn't to the extent of the universe. And that's a huge shift that happened 100 years ago. When we first started realizing that there were other planets around other solar systems, it's also these massive shifts in the way that we see what lies beyond our immediate experience. And so it seems like there's just still so much left to discover as we send more and more probes out, as we start to gather data in better ways, as we have better telescopes. It's just very...
It's a fast-moving science, it seems like.
Yeah, it seems very fruitful still.
Is fast moving once you get out there. So for the Voyager spacecraft launched in the late 70s, primary mission to study the gas giants. And then its extended mission was to study the outer heliosphere. And it only reached termination shock in the early 2000s, early mid 2000s. They crossed at different times. And then they crossed the heliopause in 2012 and 2018, respectively. And now they're going through very local interstellar space. And they're running out of power. We're not going to have much more measurements left. I think, maybe 7 to 10 years at most. But we're desperately using the latest measurements that we can with IBEX observations. As I said, the observations of the ribbon, we did a lot of modeling with different configurations of the interstellar field and basically fit a modeled ribbon to the data and found what is the best interstellar field that allows us to do that. And then that was a completely independent measurement of the interstellar field. And we compared it to Voyager in this paper in 2016, where when Voyager just had crossed, they had a little bit of data, but the field measurements they were getting were consistent with our completely separate measurements, with the ribbon correlating with this large scale structure of the interstellar field. So it is a relatively new field from the 50s onwards, but the actual high-tech measurements have just begun in the past decade and are only going to get better with interstellar mapping and acceleration probe, which is the Solar Terrestrial Probe line for NASA. 10 instruments on it. It's going to be at Lagrange 1 point, the L1 point, so it's closer to the sun on the inside of the Earth. And it's going to measure ENAs, just like IBEX, but over a wider range of energies, up to a few hundred keV, and higher resolution, angular resolution, temporal resolution. So that's 3 instruments. Then we have detector for electrons, SWE. We have a magnetometer called MAG, and a dust detector, which is, I think, one of the biggest dust detectors that will have ever been flown, because they need to be big in order to literally detect and stop a dust particle. It's one of the heaviest instruments, I believe, on the spacecraft. So these are like interstellar dust particles that we're going to be observing that get close enough to the sun. There's instruments to observe the pure solar wind particles, alpha particles, helium pickup ions, which, before with New Horizons, we were observing hydrogen pickup ions. But close to the sun, there's not so many hydrogen because they just could get depleted close to the sun. But helium, interstellar neutral helium atoms can get very close to the sun before ionizing. So that's where we create these helium pickup ions. And then we're going to observe energetic particles up to anywhere between, keV to tens of keV, MeV, maybe MeV, I don't know.
What kind of detailed information do you get from these higher energy instruments? Why are you so interested in high energy situations?
For the ENA imagers, this actually might help us understand how long the heliotail is. Because when I said before was, measuring ENAs around 1 keV, we have sort of this limiting distance that we can see down the heliotail. That's because there's a certain rate of charge exchange between the local interstellar gas that's flowing through and a particle at 1 keV, just gyrating around the local magnetic field. And they deplete much more quickly than 30 keV, 50 keV, higher energy particles. When you get above about 20 keV for hydrogen, the charge exchange cross section, which basically cross section is basically the measurement of area, basically tells you the probability of interacting with some process, could be electron impacts or electron transfer. The cross section just rapidly drops above 20 keV. So we're hoping that with IMAP Ultra, for example, which is measuring between roughly 5 keV and supposedly up to 300 keV, although the statistics might be not so good up there, somewhere in the 30 to 80 keV range, we could see farther down the tail, because the particles that would create those high energy ENAs survive longer. And we're hoping that we can bit by bit increase the distance and maybe rule out some models that cut off short tail.
Do you think that processes in the heliosphere could be contributing to the cycle of the sun, or are they totally a response to, are they totally passive? Because I'm really interested in the production of this solar cycle and understanding better what causes these polar inversions and the different appearances of the sun.
I believe it is a purely cause and effect, as in the heliosphere's reaction to the solar wind doesn't have a back reaction on the sun. And the only way that I think it could, which I don't think it could, but it affects propagation of cosmic rays, again, that are the only particles that actually make it, ionized particles that actually make it back towards as close to the sun as they can. But I don't think they really affect the solar cycle itself. However, the evolution of solar cycles, each solar cycle is different. Over the past 4 solar cycles, they've been getting weaker and weaker and weaker. And, I don't know why. I'm not sure many people do. And it's been messing with some ability to take measurements because, more activity, you get more like events happening and more events to study. But there is one thing that's common between solar cycles that we've recently found out was that this big pressure increase I mentioned earlier in late 2014, it appears that this happens at least once every solar cycle, every 11 years. And the next one is due, we believe, soon after the launch of IMAP in 2025. So hopefully we will get to measure another big pressure event and ENA response and do another study of how it affects the heliosphere structure and compare it to what we did last year.
Do you expect it to correspond to the weakening solar cycle in the sense that the pressure will be weaker if the solar cycle is weaker, or does it not correlate that way?
I think there is a correlation to that. It's sort of like the number of sunspots is usually just an indicator of maximum or minimum, but also it's an indicator of activity and how much the properties of the solar wind that is emitted from the sun. Like especially the polar coronal holes is almost a big sunspot, but I technically not. That emits purely fast wind because those are open field lines. There's nothing holding them back. The sunspots actually have closed field lines, so they're actually holding back the solar wind and on average they go out slower. So each solar cycle can have a different pressure that it emits throughout the cycle, and also this big pressure event could be next time could be a mini pressure event, or it could be a lot larger, but probably not.
Is the pressure event a tension release of some sort in the transitioning of the polarity of these stars?
I have no idea. One of my colleagues wrote a study on that. The timing was these occur every about 11 years. So not directly just every 22 years, but they happen during solar maximum, I believe. So it could be interactions of fields and buildup of sunspots or something like that, and overreaching my expertise, but could be related to that, yeah.
Does the stuff that comes out of the sun change when the pressure increases, or is it just more stuff coming out?
It could be more stuff, less stuff, faster. They come out faster,
but the
slower.
composition of it is the same, like in terms of elemental composition.
I believe so, yes.
Interesting.
The ratios of the elements could be a bit different, but I don't think there's ever like a new element or one completely goes away.
And so when we think about the Earth in context of all of this, does your modeling reflect back eventually on what's happening on the Earth, or is it mostly focused at the interface of the solar system with the interstellar medium, and so it's so far away that it's not being fitted to Earth conditions?
So it could be a two-way street. Lately, we use observations of solar wind around Earth as our boundary conditions, no longer point source, but as our boundary conditions for a dynamic simulation of the heliosphere that will then create a very dynamic heliosphere, like shapes, the boundaries moving in and out, ripples on these surfaces. And the classic thing is how does that cause filtration of cosmic rays, and then that'll affect stuff near Earth. But in my research, I would say it's more about leading to our understanding of our solar system and the heliosphere's place in the interstellar medium, and A, what we can learn about that, and B, what can we learn about with future interstellar observers like Voyager.
Mm.
It takes step by step to get new interstellar spacecraft built and launched, but I'm sure we're going to get another one soon enough. So it's more about the exploration outwards in my mind.
It seems like the other disciplines would be very interested in this work, though, especially climate scientists and people looking at cosmic rays and looking at how the Earth, well, yeah, really just how to, buttress ourselves against future events and how to detect those early and imagine how because this has been really important, right? In the heliosphere itself, you mentioned this at the beginning, is instrumental to the thriving of life on Earth, right?
Mm-hmm.
We would be kind of toast without it. So if it's weakening at different points throughout history, that's going to play a big role in the appearance of life on Earth.
Yeah, like, do you worry that you will one day uncover some evidence that demonstrates the arbitrary cruelness of the universe when it comes to the protectiveness of the sun?
Not in my lifetime. I think the people that will first realize that is the people that actually look at the sun surface itself and say, nothing's happening, guys. There's no sunspots. Uh-oh. Or the other extreme, huge solar flares or events like that have to be aimed right at Earth that can cause, and they have caused satellite disruptions or on-ground disruptions.
Mm-hmm.
And
yeah, it seemed
like
we talked to
Madhulika?
Yeah, Madhulika Kuhartakarta, who is working.
She was the director of the Living with a Star initiative at NASA, and after completing her work there, she had basically started developing more interdisciplinary studies that connected Earth conditions to solar behavior. And I remember when we talked to her, they had just had a conference at Ames where they were starting to look at the relationship between solar cycles and seismic activity.
Oh, interesting. Yeah, I know there's a lot of Sun-Earth research in Living with the Star program.
And I think that we have to have the belief that the sun is going to always look the same, because it's hard to live if that's not the case, right? We believe that billions of years from now it'll burn out or something, but that's so far in the future that it's off the page. You don't have to worry about it. But when it comes to small shifts over the course of 11 years, 22 years, 100 years, then that suddenly becomes something that is much more impactful. And because it's so complex, it's hard to create models that accurately and effectively wrap it into the way that we see our position on the Earth and the development of life and everything else. And
especially so if you want to predict 10, 20 years in advance, at least.
Yeah, exactly. And so when you look at when you see people modeling planetary conditions, and they model it largely as, planet and sun as it is right now.
Point source.
Yeah, exactly. Like, if you're not really looking at, well, this is an object that evolves and shifts and changes, then it's easy to look at the data that's coming out and be like, look, that's a model that doesn't have the appropriate boundary conditions for where it can go. You're limiting it to something too small. And so it's cool that there's so much work that's being done to expand our understanding. And these cycles that you're seeing that are taking, a decade to propagate around the entire system, and that are these slow moving, you would expect it to have some kind of hysteresis on everything else that's happening, right? Because since it's an electromagnetic system that's feeding back onto itself, that you would be eventually, through enough years of observation, starting to see these very, very complex, long-range interactions between the sun and what's beyond it and the planets. And it's so cool and so big.
Yeah, one of the neatest things in sort of modeling a very sophisticated heliosphere is if you take a time-dependent solar cycle model of the sun and very high resolution simulation, very large box simulation, and it produces a heliotail. One of my colleagues, Nick Pogorelov, he produces a heliotail that's almost 3,000 AU long. If you look closely at it, this length of heliotail has history of all of the previous solar cycles, of dozens of solar cycles, because they each have their own imprint of, well, at solar cycle 22, it had this minimum with this fast wind going out, it had a certain density and temperature, and then it reached a maximum, and then next minimum, maximum. So you see these changes in density and temperature splotches all the way down the tail. The tail is then squeezed like that by the interstellar magnetic field the further it goes. And then eventually it just squeezes into this narrow plane, and then I guess just dissipates and mixes with the local interstellar medium. So in my sense, that's sort of what I call a very good look at the historical activity of the sun in terms of the heliosphere.
Is there a mission that's specifically traveling down the tail to be able to get these sort of tree rings off of it?
No, unfortunately not. That would be nice. There have been some studies on an interstellar probe to follow up from Voyager that would take more, hopefully better resolution or dedicated measurements, because Voyager did way beyond than what they expected. But I think the chances that they would want to launch it down the tail is less, because they want to be able to survive long enough to reach the interstellar medium, the pristine, and try to actually measure those pristine properties, because the Voyager spacecraft will never do that. They're still within the part of just outside the heliopause that is strongly influenced by the bow wave, basically ahead of the heliosphere.
So they're protected.
Not protected by anything, really. It's more of they're just measuring plasma properties that are distorted, compressed density. The field lines are draped now that they cross the bow wave. So they're not going to tell us actually what are the pristine values of speed and density, temperature, field, beyond the influence of the heliosphere.
Are you saying that's just because they're going to run out of steam? They won't be able to return measurements? I see.
Yeah, they're running out of power, and they're one by one turning off instruments as we speak, deciding that. And going to leave on the one instrument with the best data, I think. Magnetic field generally is the best data to use.
Is there any difficulty in transmitting communication signals across this boundary?
No, I don't think so.
Interesting.
The only difficulty is the time. And sometimes they, I believe, had, I don't know, better word, conniptions, like dropouts or something. But I don't. It's usually either the receiver on Earth maybe has an issue, or the spacecraft maybe has an issue. But the actual signal, no. The data rate's pretty low because it's so far away. But it's
Will it
still,
pose any challenges to spacecraft that are hoping to, one day travel to other stars? Is this a legitimate barrier to? Is there dangers to humans in crossing this?
I would say no, because we think of this barrier in terms of like, okay, when I say the temperature of the heliosheath, and I tell you the temperature is a few million degrees, you would tell me, okay, I don't think I could survive in a spacecraft traveling through that for very long. However, the number of particles per cubic centimeters, the usual units I think of, is 0.001 or something like that. There's so few particles that have these high energy, on average, million Kelvin temperatures. They don't actually, there's not enough particles to transfer the heat to you or the spacecraft. So that's not actually an issue.
Yeah, it's always so confusing to me when we talk about the temperatures of these processes, because you really don't have to consider density on Earth when we're
it's
speaking about
normalized. Temperature is just a mean energy of however many particles you measured. Could be one is a bad measurement. Two, I think, is still a bad measurement.
But every once in a while, you're getting pummeled with a really hot particle, essentially.
Yeah, that's basically where cosmic rays come in. When you get far beyond that, cosmic rays can be a detriment to spacecraft. They could, I don't know if you've heard the phrase flip a bit. Just one cosmic ray can enter electron export and literally change a 0 to a 1 or something. And could cause a glitch. The rarity of that, I'm not really sure, but there's a lot more cosmic rays outside the heliopause than inside. So
interesting. Are people scared of bit flipping here on Earth with our own systems during a storm of some sort? Supernova? Nearby?
Nearby supernova, I think I would be more worried about other things than a bit flip. Oddly, that has occurred to some people I've worked with over the past years. Like, sometimes in a funny way, like, man, my code is crashing, or there's this bug somewhere, and then the next day it works. It must have been a cosmic ray yesterday.
Nice. I'm going to start blaming our video editor on cosmic rays.
Yeah, it's true.
It's also completely unpredictable.
So you said that if there's a nearby supernova, you'd be more worried about other things than cosmic rays.
Well, cosmic rays would be one, but if it's a nearby supernova, like how nearby?
Well, Galileo's was it Galileo's supernova? There was one that was observed in the maybe late 1500s, 1600s, I think. Because when we were talking about the Maunder minimum, I was immediately thinking like, I wonder if it's related, but I don't know how far away that thing was. But we haven't seen a supernova in our galaxy since the advent of modern astronomy, unfortunately. I mean, maybe for the better, actually. But
there was supernova observed
in our galaxy.
Oh, in our galaxy.
Yeah, in our galaxy. Yeah.
No supernova has been observed in the Milky Way since 1604.
Yeah, 1604. That's what made me think about that Maunder minimum. I wonder if it was related somehow. This completely half-baked idea.
Who knows?
Who knows?
Interesting.
Yeah, what do you think we would expect if there was to be a supernova in our vicinity?
What if Proxima Centauri supernovaed? Would we be cooked?
Man, I should bring in one of the astrophysicists, but it's a Saturday. No one else is here. I
I mean, it must be,
definitely
right?
think
Like,
it would influence us, yes.
because I mean,
For
like,
better or for
the
worse.
size of a supernova, several light years across. If we
Yeah.
if we're only 4 light years away, we'd probably get cooked. All right, so
Either that or very, very influenced by cosmic rays that are accelerated by the supernova shock. Yeah.
Yeah, because they sort of resonate around in there. Isn't there some sort of process by which they're amplified in supernova explosions?
Yeah, I think it's probably diffusive shock acceleration. We have that happening in our solar system too. But obviously that whatever process they undergo is they gain a lot more energy.
Well, let's cross our fingers that we don't have to deal with that anytime soon.
Indeed. I mean, this has given me a lot to think about. I think that I have a better picture of the scale of the events that the sun is influencing. I have a better sense of what's happening at the very edge of the solar system. I guess the last thing that I haven't fully packed away for myself yet is what's in between the heliopause and the interstellar medium boundary.
So the interstellar medium, just think of it as flowing along nicely, not being disturbed by anything. And it obviously is coming up to an obstacle, which is the heliopause. It will undergo a shock if it was supersonic, just like I said earlier about the solar wind, or a bow wave. Now, the details in determining if it's a wave or a shock depend on other highly nonlinear processes with neutral particles, but this region of space where the heliosphere at least significantly influences the local interstellar medium is still a few hundred AU away from us. And it would take, the Voyagers are at 150-ish. They would have to travel another 200 AU tops. They can't survive that. So it's a very loose, I wouldn't say there's really a boundary between the pristine interstellar medium and the influence of this heliosphere or sun on the interstellar medium. It's a gradual change. And you just have to get far enough out using, I don't know, your best guess, or you look at trends in models to say, okay, the density has gotten to the point of our initial boundary condition, so it no longer influences it.
It's like, I think about it, there's this one swimming hole that we go to where it's this really deep pool of water, and as you move farther downstream, you get closer and closer to a constriction that leads to a series of rapids. And you actually, on the surface of the water, can start to see where the influence of the rapids begins, as there's this narrowing and speeding up of the current. And it seems like that's what's happening at this interface.
I don't think that is happening at the interstellar medium's interaction with the heliosphere up front, but actually that could be happening inside the heliosphere itself. So as the solar wind plasma crosses the shock and is diverted away from the heliopause and flows down the tail, it could actually speed up along the flanks into the tail because of the change in volume. Just like what you were describing, you can have a pipe that gets smaller and then faster flow. And there's some evidence in IBEX data that suggests that's happening on the flanks.
I was thinking more where there's a point where you're saying that there's an area of pristine interstellar medium, and when I look
Mm.
at the river, there's a place where it's still not yet interacting with the rapids, and so that would be the pristine area versus where it's actually there is an interaction, and that's no longer the sort of the bulk. You wouldn't be able to model it the same way that you would model the bulk pool or the swimming hole. Like the bulk behaves differently from the interface. And so there's a bulk of interstellar medium, and that's the pristine area versus the mixing that's
I
happening.
guess the question is like, how much does the bulk interstellar medium interact with itself? Like, how long range are the interactions? Are sound like waves being propagated? Are there collisions that are propagating throughout the ISM normally?
Close to the heliosphere, we would call it a collisional plasma, I think. Not. It's kind of weird because then when you get into the bow wave, it's a higher plasma density, so higher collisional, but then the temperature gets higher, so it kind of offsets it. But what ends up happening is almost exactly what you're trying to describe, is whether or not we actually do produce a bow shock or not. That's still a bit of a debate between people, because one thing that affects the sound waves in the local interstellar medium is actually, you remember I said there's these neutralized solar wind particles that just ballistically travel outwards that create the ribbon. Well, some can travel very far and go beyond the bow shock and then embed themselves in the what we thought was pristine interstellar medium, change the thermodynamic properties of that area of the interstellar medium, making it hotter, making it more subsonic, and then we won't have a strong bow shock anymore. So it's a quite a multi-step nonlinear process between ions and neutral particles going in and out of the heliosphere that actually determine the size and structure of the interaction itself. And that's sort of the basis of what I do most of my research on. Yeah.
And it seems like it would be a dynamic structure based off of everything that we've talked about.
The bow wave?
If it's the product of the interaction of the solar wind and how far it's going into the interstellar medium, then changes in the the point particle that's producing the solar wind.
Yeah, I don't think it's as dynamic as you might think, because again, these particles are high in energy but rarefied. So they would just kind of globally change things, but the neutral properties on average over a solar cycle wouldn't change that much to affect the whole bow shock, I think, but that's just conjecture.
Looking towards the future, what are some of the biggest questions you have about the heliosphere that you hope to answer in your career? Hope somebody will answer, at least.
I want someone to show me that the heliotail is at least 1,000 AU long. I want to see that. And if it's not, I'll be interested to see why. I would really like to get higher resolution maps of the structures of these boundaries, specifically how they change over time at smaller and smaller scales. Because with IBEX, it was a push to get these high resolution maps of these ripples on these heliopause and termination shock, but we can only do it for a part of the sky where we had a strong enough signal change to say that, okay, bam, this is when this event happened. I'm hoping that with IMAP, we can answer both questions at once, hopefully. with high energy particles for the tail and higher cadence and resolution to look at dynamic changes in the boundaries. So I'm hoping that we can get a full picture, high resolution full picture of the boundaries. So far, we've gotten low resolution picture averaged over a solar cycle, or high resolution picture at a very specific point in time. We got to connect those somehow. That's what I'm looking forward to.
And I mean, getting a movie of that would be a really satisfying visualization.
And I'm going to try my best over the next 10 years.
Amazing. I look forward to seeing it.
Yeah, I'm looking forward to seeing what comes out of your research.